Thank you very much. Thank you very much for the invitation. In the book, Rigid Local Systems, Nicholas Katz solved zero peak curvature conjecture for rigid Fuchsian ordinary differential equations. And his notions and results also are very useful for theory of Fuchsian ordinary differential equations. And it is extended to irregular singular case. And I have been interested in extending the theory for higher dimensional case. So in this talk, I will briefly review the one-dimensional cast theory, and then how to explain how to extend higher dimensional case, and explain several examples applying the higher dimensional cast theory. So first, one-dimensional case. So it's 70, 80 something. No. A local system is rigid if it is uniquely determined by the local monotomy. This is the original definition of rigid. Local system is a monotomy representation of a differential equation, or representation of the fundamental group. We consider as some Riemann surface minus several finite points. And then, so if we remove some points, and then monodromy are encircling up this point, give the conjugacy class of the monodromy is called a local monodromy at this point. And this is a notion for a local system, but today I will explain additive version. Additive case. So we consider a system of differential equations where Aj is n times n constant matrix. And small aj are mutually distinct points in C. And we set Azo to be the minus of the sum. This is the residue matrix at infinity. So this system has a regular singular point at A1 to AP and infinity. So I call the rank of this system. And I call it A. And in additive case, in this case, A is rigid. It is determined by the local behaviors of solutions at the singular point. Uniquely to isomorphisms. And in other words, this is the simultaneous conjugacy class of the collection of the rigid matrices. A simultaneous conjugacy class is uniquely determined by the set of conjugacy classes of each matrices. And Katz defined the index of rigidity it is given by the formula. I use iota to denote the index of rigidity. Iota is 1 minus p times n squared plus 1 to p dimension of the centralizer J from 0 to P. This is a numerical value, and it is known that if iota, if A is irreducible, then iota is at most 2. And in this case, if A is rigid, then iota, A is rigid if and only if I is 2. Iota is 2. And 2 minus I the number of the accessory parameters. A typical example is a rigid friction system is a Gauss hypergeometric ones. And for Gauss hypergeometric case, yes. Yeah. For monodromy, M, E, M1, M0 is identity. These matrices of corresponding to the local monodromy, local plus one loop for each singular points. And this relation comes from the triviality of the product of these loops. And in additive case, the sum of all residue matrices becomes 0. And Gauss hypergeometric case, we have n is 2, and p is 2, and aj, each aj is 2 by 2 matrix, and we assume that the eigenvalues are mutually distinct. So, the spectral type I use spectral type means the partition which represents the multiplicities of the eigenvalues. So this spectral type is 1, 1. And then a spectral type is the partition of n, which represents the multiplicities of the eigenvalues. For simplicity, we assume that all matrices are semi-simple. We can also consider the non-semi-simple case, but in this talk, I restrict to the semi-simple case. And if if AJ has two distinct, so we also assume a non-resonance, which means there is no integral difference between distinct eigenvalues. Then dimension of set AJ is 1 squared plus 1 squared 2. In general, if the spectral types is M1 to ML, then the dimension of the centralizer becomes this square sum. We can explicitly compute this index of rigidity for a given tuple of matrices A1 to AP, A0 to AP. And then in this case, I is 1 minus 2 times 2 squared plus 1 squared 2 plus 2 plus 2. There are 3 singular points. For each singular point, the dimension of the centralizer of the residue matrix is 2. So this is minus 4 plus 6 is 2. And this is rigid. And the result, the Gauss hypergeometric is rigid, is obtained by Riemann. Famous result. But for any Fuchsian system, I call this a Fuchsian system. For every Fuchsian system, we can compute the index of rigidity, and we can know whether it is rigid or not. And for so next, the main notion of Katz theory is middle convolution. And I will define two operations. Yes. Sorry? Yeah. To compute the index of rigidity, to show that to show this result, I think similar. A little complicated in multiplicative case, but almost similar, I think. So, I will define two operations. One is addition, which we take a tuple of complex numbers, and then addition by alpha is which sends aj to aj plus alpha ji. So for a given function system, we replace aj by aj plus alpha j. And this is analytically corresponds to the change of solutions to this gauge transformation corresponding to the addition. And the second one is the main operation, middle convolution. And we take up complex parameter lambda, and middle convolution with parameter lambda sends a tuple of matrices to another tuple of matrices. Later, I will give some explicit cases to give BJs, but I don't here give explicit realization, but only explain analytic meaning. And roughly speaking, Z so we obtain another function system with residue matrices Bj. And this solution Z is something obtained from the original solution Y by this integral transformation. This is a very roughly explanation, but it is noted that you can get a solution of the new transformed equation by integral transformations. And a middle convolution has many remarkable properties. And first is additivity. A composition of MC lambda and MC mu is essentially the MC with parameter lambda plus mu, and MC 0 with parameter 0 is the identity. So middle convolution is invertible. And also MC lambda keeps the irreducibility. Sorry. To get set of independent solutions, you must choose this one. But if in order to be a solution of this system, delta can be taken arbitrarily in a homology space. Then, the main theorem of Katz is any irreducible rigid Fuchsian system is sent to a rank 1 system, rank 1 equation by additions and middle convolutions. So by operating, in general, middle convolution will change the rank. It may increase or decrease the rank. So by operating middle convolution for a given system, you may decrease the rank. And if a system is rigid, you can decrease the rank to 1. And also, since addition and middle convolution are invertible operations, then if you start from rank 1 equation and operate Katz operations, then you will always get a rigid equations. Yeah. So it seems that. Sorry? Any reason? So BI may be bigger or smaller. Sorry. I will give many examples in that section too. Okay. So in Gauss case, there are 3 singular points and of 1 as the spectral type of residual matrix. So we denote like this. This is Gauss one. Okay. There are 3 singular points, and each residual matrix has spectral type 1, 1, 1, 1, 1, 1. And by middle convolution, so I calculate this value. D is D minus 1 minus P. Sorry, Yeah. So I calculate in some way some number d, and in this case I have d is 1. And remove this one, we can get. So this is, and this represents the rank 1 equation. There is a way for arbitrarily given spectral type, you can calculate number d. And if the number d is positive, then you can reduce for each component of the spectral types, one component. From one component, you can reduce d. Then you will get rank n minus d new equation. Okay. Then you operate addition next time. Then you will get so for a given spectral type, you compute d, and if d is positive, so you can reduce the rank. Then now I operate addition. This is module convolution, and this is addition. Then so addition is operated for increase the number d, and then after addition we compute next d, and if d is positive, we can also reduce the rank. And if the spectral type was rigid, then this operation ends at the rank 1 case. They say the meaning of this theorem. You can choose cleverly to reduce. If you to take arbitrary lambda, d will not so small. But if you choose lambda cleverly, you can reduce d. You can make d bigger. I wanted to explain higher dimensional case, but if you like, I will explain one-dimensional case more in detail. Yes, it's good. So okay. I will give one example. Yeah, this one. Because they are a function system of spectral type 2, 2, 2, 2, 2, 2, 3, 1. Namely, this is a function system. And by a Möbius transformation, we can send four singular points to 0, 1, infinity. So this is a1 over x plus a2 over x minus 1 plus a3 over x minus another singular point, y. And the spectral type of A1 is 2, 2. A2 is 2, 2. And A3 is 3, 1. And A0 is minus A1 minus A2 minus A3. And I assume A0 has also spectral type 2, 2. They are 4 by 4 matrix with two different singular eigenvalues, and the multiplicity was 2, 2, 2, 2, 3, 1, 2, 2. And I calculate the index of rigidity. Iota is 1 minus 3 times 4 squared plus 2, 2 means the dimension of the centralizer is 2 squared plus 2 squared. And these are 3 plus 3 squared plus 1 squared. And this is minus 2 times 16 plus 8 times 3 plus 10. And this will be 2. I will not calculate, but it will be 2. So this is rigid. And I start from this spectral type, and I calculate D is 3. Yes, yes. This is 1 minus P. P is the number of the finite singular points times the rank plus I take the biggest component of each one. And this 2, 2 is the spectral type of A1. And I assume that the among two eigenvalues, one is 0. And I regard 2 is the multiplicity of eigenvalue 0. Also, this is this corresponds to the 0 eigenvalue of A2. Also, this 3 is eigenvalue 0 of A3. If the multiplicity of 2 or 3 was not 0, then you can operate addition to send the maximal multiplicity eigenvalue to 0. Okay. And this 2, last one, is the multiplicity of the eigenvalue of lambda. So eigenvalue of this corresponds to an eigenvalue of A0, and I denote it lambda. And if you take lambda as a parameter of middle compression, you can calculate this. These three are multiplicity of each eigenvalue of residue matrices, and this last one too is a multiplicity of the eigenvalue of the residue at infinity. And I take the lambda as a parameter of middle compression. Then you can compute this. This is minus 12 plus 13 is 1. So I can reduce 1 of this rank. So I subtract 1 for each component. So I have 1, 2, 1, 2, 1, 2, 2, 1. So we get a rank 3 equation. And of course, middle compression keeps also the index of the rigidity invariant. So this is also rigid one. And I change 2, 1, 2, 1, 2, 1, 2, 1 by addition. This one is not correspond, this 2 that it, does not correspond to the eigenvalue 0 of the result of the residue. So I operate some addition. This is middle convolution to make the maximal multiplicity eigenvalue to 0. Then I calculate D. In this case, this is 1 minus 3 times rank 3 plus 2, 2 times 2 times 2 times 2. This is minus 6 plus 8 is 2. So I can reduce the rank by 2. MC mu 1, 1, 1, 1. This is the rank 1 equation. So this equation can be obtained from rank 1 equation by the operating inverse of the 3 operations. Yeah. So So this is the main frame of Katz theory, and I have a way to extend the middle convolution for a higher dimensional case. And for simplicity, I consider a higher dimensional case by for simplicity, I restrict to KZ type equation. Which is given by this Pfaffian system. Aij is n times n constant matrix. And x1 to xn are variables. And the integral, so since this is a collection of ordinary differential equations, I set Aj to be Aij. This Pfaffian system is a collection of ordinary differential equations in Xy. Okay. Then we should have integrability condition. namely dxj of d dxi should be dxi of du dxj. And this is the relation of residue matrices, which is A, I, J, A, K, L commute, and A, I, J, A, I, K plus A, I, J commute. I, J, K, L distinct. Sorry, JK. And we assume that one such KZ-type equation is given. Then the middle completion I denote it by U, and this equation UI. Okay. The middle convolution for the ordinary differential equation UI, this is the Katz operation, can be extended to an operation of U. We can extend the middle convolution as an operation for KZ-type equation. And also in this case, we have several similar good properties for middle convolutions. And since I don't have many time, so I will give an example. I use this example of rigid ODE. So first we start with a rigid Fuchsian system. And operate middle convolution and addition several times. You will get rank one equation. Rank one equation. This is the result of Katz. And I make a Pfaffian system for this rank one equation. du is sum of j1 to p alpha j d x minus aj over x minus aj u or y. I regard the position of the singular points as a new variables of that equation. And since this is rank one, the integrability condition is automatically satisfied. So this is integrable. And I operate, so I denote this operation MC lambda xi and call it a middle convolution in xi direction. Okay. Then I go back by using the extended middle convolution, MC, X, lambda, etc. And I will get something quasi type equation. So if you start with a rigid function system, you can operate Katz operations to get a rank 1 equation and regard it as a Parthian system, as positions of singular points as new variables, and operate the Katz operates middle convolution in higher dimensional case with in x direction. Then you will get integrable KZ type equation, and whose x equation coincides with the original rigid equation. So this is a way to get integrable KZ type equation. And these conditions, integrability conditions, are you can. So it is very difficult to find good tuples of Aij satisfying this and satisfying irreducibility. So this is a very effective way to get a tuple of residues Aij satisfying integrability condition and also irreducibility. And by using this example, we start from 2, 2, 2, 2, 2, 2, 3, 1, rigid equation, and rank 1 equation, 1, 1, 1, 1, and regard it as a Parthian system, and go back to equation. So I will write this. The result is written in this way. A1 dx over x plus A2 dx over x minus 1 plus A3 dx minus y over x minus y plus A4 dy over y plus A5 dy over y minus 1 u. A1, A2, A3 are original residue matrices, and A4, we have an explicit way to get A4 and A5, and they satisfy these integrability condition, and also it is irreducible. And I give the spectral types. So the point is that the result is rank 1. Then we have always rank 1 integrable ones. And if you have a rank 2 equation, and if you have a way to make it an integrable system with satisfying integrability condition, then you make it, but it is, in general, it is very hard to find good residues satisfying this. Ever rigid ones. So if you are given an irreducible integrable one, then they satisfy this condition. But we have no way to get such KZ type equation. To get this one, you must solve this equations for matrices under the condition they give irreducible ones. There is no common non-trivial invariant subspaces. It is a very difficult problem. I think we have no way, general way to get this one, such two problems. This is a kind of monotony deformation. Yeah, you're right. Yeah, yes. Deformation is an extension to integral system. In this case, we get an integral system which whose equation is ordinary differential equation. So this is a deformation of the rigid equation, right? Okay. And the most yeah. I think almost all known integral systems are constructed from solutions, integral representation or power series solution. And I think many of them come from rigid ones. So it is very interesting to get a non-rigid integral KZ type equation. And I wanted to propose one way to get non-rigid ones if time permits. So I will tell later. And in this case, the spectral type was 2, 2, 2, 2, 3, 1. And these are also two spectral type 2, 2. So this is extension of middle compression, and it is very interesting to combine Katz operation with restriction operation. So for higher dimensional case, we can consider a restriction to a singular locus. And in this example, singular locus is given by this figure. X is 0, X is 1, Y is 0, Y is 1, and X is Y. And restriction to singular locus means take holomorphic solution which are take solutions which are holomorphic on a given singular locus, and compute the system of satisfied by these solutions. This is a restriction of singular locus, and we can get so I will also explain by using this example. Since A3 is spectral type 3-1, I assume that eigenvalue of multiplicity 3 is 0. Then this means there are three-dimensional holomorphic solutions on this singular locus. Okay. Then I write AJ, BJ, something. I partition each other residues as 3-1 partition. Then restriction to X is Y is given by this equation, dV dx is d1 to 4 plus In this case, in this particular case, the restriction to singular locus x is y is given by this explicit ordinary differential equation. Bj's are 3 by 3, and this is rank 3. And it is remarkable that spectral type of this restriction system is 1, 1, 1, 1, 1, 1, 1, 1, 1. The index of rigidity is 1 minus 2 times 3 squared plus 1 plus 1 plus 1 is 3. 3 times 3 is 0. This is non-rigid. And in this way, by combining, we start from a rigid ordinary differential equation and operate higher dimensional Katz theory and combine it with a restriction operation, then I get a non-rigid differential equation. And as I explained, a middle comparison is an integral transformation. And we start from rank 1 equation, which has a explicit power functions solution. Then the solution of the result of Pfaffian system has an integral representation of solutions. And restriction is only take restriction. So this non-rigid equation has an integral representation of solutions. It is very exceptional ones. And it is known that this is, it turns out to be Dotchenko, RTS equation, which is found in the conformal field theory. And since I have no enough time, I prepared many such examples, but I stopped to give ones. But what I wanted to say is, if I start from, so there are many rigid equations, and we can operate Katz operations to go to rank 1 equation and take regard it a Pfaffian system and operate higher dimensional Katz operation. Then I will get a higher rank integral irreducible Pfaffian system, and take several restrictions to singular locus, and you may obtain non-rigid ordinary differential equation. They all have integral representation of solutions. So this is a very explicit and effective way to get non-rigid integrable representation, having integral representation equations. So please. These explicit operations are written, you will find in a book, in the lecture note in Math 2271. You will find how to make these A4, A5 matrices and how to take restrictions. And this is, so this game can be enjoyed for any people. You can make many non-rigid equations with integral representation of solution by operating this story. And lastly, I wanted to say that how can we define the index of rigidity for KZ type equation. So for ordinary differential case, the index of rigidity is corresponding to a local system. And in one-dimensional case, the fundamental group of P1 minus finite points are free group. But in this KZ case, so generators of the monodromy are loops encircling each component, irreducible component of singular locus. And for example, this, if two locus are normally crossing, then these loops commute. So the fundamental group has many relations. So it makes the definition is complicated. So once I considered how to define the index of rigidity, but I have no idea. If you succeed, then the index of rigidity will be given as a formula in terms of the number, rank, and the spectral types of each residue matrices. And then, and if you see the index of rigidity, you can, it will give a criterion for rigidity, but this is a very interesting problem, but I have no idea. And lastly, so I said that to find explicit tuple residues satisfying this with irreducibility is very difficult problem. There is no general way to obtain these ones. So one problem is we prescribe the tuples of spectral types corresponding to each Aij and ask whether there exists integrable, irreducible KZ-type equation which realize the prescribed spectral types. This is very difficult problem, and I think there is no general way to attack such problem. And this index of rigidity will be concerned to this problem. Do you understand? Okay. I wanted to show many more examples, but I have, so I started that from 2 o'clock. I will stop here. Thank you very much.
Linear algebra?
Yeah, yes, linear algebra. I don't know. I think this program corresponds to the representation quivers. So yeah. So so there is, I think, no general theory for obtaining representation quiver. So this my idea is to use higher dimensional Katz theory to produce explicit examples, solutions. Yes. Yeah. Middle compression is essentially an Euler transform of integral transform, known as Riemann-Leibel integral or fractional derivation. So it is not original of Katz, but it's known from very long time ago. And the Katz, so we can always consider Riemann-Leibel transform of a solution of differential equation. And it is very difficult to describe the differential irreducible component of the differential equation satisfied by the result of the Riemann-Leibel integral. Katz did it. If you have a irreducible differential equation, and you can always transform it by Riemann-Leibel integral transform, you will get a function. But we want to know the differential equation satisfied by these integrals. And we also ask the irreducibility. So this is very difficult problem, and Katz did it, I think. How to make the irreducible. So usually, if you increase the rank, then you will always get the differential equation satisfied by the result of Riemann-Leibel integral. But the system is usually reducible. It is difficult to find the irreducible component of the reducible equation. This is the middle compression.